Welcome to this lecture. My name is Mark Scythian. The date today is August 16th, 2025. So in this lecture, we're going to calculate the area of an equilateral triangle within a 300 square inch circle. So this is utilizing the fundamentals of analytical geometry and trigonometry. So the first step is we have to access the equation for calculating the area of a circle. So that is A is equal to pi r squared. So we can redefine pi r squared as also diameter divided by 2 quantity squared. And then we can also redefine that once again so that we square d over 2, d times d divided into 2 times 2, so d squared over 4. And then we can further combine the equations such that we have pi times d squared divided into 4. And then convert the equation algebraically into a one-line equation. So it is a times 4 is equal to pi times d squared. So that becomes 4a is equal to pi d squared. And then simply solve for d squared. So algebraically rearrange as 4a over pi is equal to d squared, and then we solve for d by finding the square root of both sides, so that cancels out the d squared into d. So then the diameter of a circle is equal to the square root of the ratio of 4a over pi. So the diameter of a circle is the square root of 4 times the area divided into pi. So then we apply the values, or the value of 300 square inches times 4 divided into pi, and its output answer, its square root. So then we calculate a circle diameter of 19.54 inches. So if we divide this value into 2, we can then calculate the radius of the circle. So since we're dealing with an equilateral triangle, all sides have equal values and all triangles are equal to 180 degrees, so 60 degrees on each side. So we can bisect the equilateral triangle based on the diameter that we calculated. So again, if we were to bisect this equilateral triangle, then we will have two 30, 60, 90 right triangles. So this is the equilateral triangle vertically bisected into two 30, 60, 90 triangles. So the next step is to find the ratiometric relationship of all three sides of a 30, 60, 90 degree right triangle. So we can start with the 30 degree side, and its opposite side is identified. Then the perpendicular leg is the adjacent side, and then the diagonal connector is always the hypotenuse. So we can assign a value of 1 to the opposite side, but first we have to define the trig function. So tangent is opposite divided into adjacent, sine is opposite divided into hypotenuse, and cosine is adjacent divided into hypotenuse. So if we were to apply the tangent of 30 degrees is equal to 1 inch divided into a, and carry on with sine 30 is 1 inch divided into h, we can then solve for the adjacent side if the opposite side is 1 inch by dividing 1 inch into the tangent of 30 for the adjacent side and 1 inch into the sine of 30 for the hypotenuse side. So for the adjacent side, we would get 1.73 inches, or the square root of 3, and the hypotenuse 2 inches. And just to validate if the hypotenuse is correct, we can also solve for h using the square root of 3, or the adjacent leg length, into the cosine of 30 degrees, and we do get 2 inches for the hypotenuse side. If the opposite side is 1 inch, therefore the adjacent side is the square root of 3, or 1.73. So based on this ratio, we already have the radius 9.77 inches. We could divide 1 inch into the square root of 3 and get the ratio of what the opposite leg will be at a certain value of the adjacent leg. So we can equalize the radius as the adjacent leg, then times 0.57735. So the opposite leg, or the base of the left end side upper area triangle, is 5.64 inches. So now the next step is we're going to isolate this trapezoidal shape here. And so we can get a better detailed analytical view. And if we were to place a hypotenuse across these two 90-degree angles, this would then create a 45, 90, 45 right triangle. And we know that all triangles have 180 degrees. So if you were to add the first angle, 45 degrees, to 90 degrees, we'd calculate 135 degrees. So we then subtract 180 from 135, and we would indeed get 45 degrees. So the third angle has been calculated. And so then we can isolate this 45, 90, 45 right triangle here into another isolation set. So we can further analyze it in clarity. So this time we're also going to find the ratiometric relationship of all three sides of a 45, 90, 45 triangle, if you haven't already memorized it. So if not, you can always use trig to mathematically prove it. You can just take the tangent at 45, because we're going to use this angle for the opposite side, and assign 1 inch for the opposite side, and then divide it into a, just like we did with the 30, 60, 90 triangle. So if we solve for a, it's 1 inch divided into the tangent of 45 degrees, which is also 1, and this equates to 1. So we know both the adjacent and the opposite legs of a 45, 90, 45 triangle are equal values, a 1-to-1 ratio. And then of course the value of the hypotenuse is 1 inch divided into the sine of 45 in this configuration. So then we get the square root of 2, or 1.41. So we can also prove this using Pythagorean theorem. The adjacent opposite legs are a or b, or b or a. We could square a and b to equal to c squared for the hypotenuse, and then equal 2 with c squared. So then it becomes a square root of 2, or 1.41. So we prove that the adjacent and opposite legs have a 1-to-1 ratio only when dealing with a 45, 90, 45 degree triangle. So based on that, we know what the adjacent side is. Now we know what the opposite side is, because they're of equal values. And so this equivalent opposite side is the remaining altitude for the height of the triangle, for which we add to the radius to complete the total height of the triangle. So we calculate a triangle height of 15.41 inches. So next, we can isolate this trapezoidal shape here once again. And this time, we're going to isolate the altitude outside of the square values. This is drawn a little out of scale, but this is actually a square. So all four sides, the vertical and the horizontals, are all 5.64. So we have to find the remnant distance of this opposite side here to then know half of the base, which is bisected, for which then we can multiply times 2 to get the total base length. So again, we focus on just this 30, 60, 90 triangle isolated here. And we can actually prove that the last angle is also 30 degrees. So it is also a 30, 60, 90 degrees, and just doesn't look like one, but it actually is. So I have to be careful that we don't just go by what things look like, but we actually mathematically prove their numeric values to absolute certainty. So yes, that is confirmed. It is a 30, 60, 90 degree 30, 60, 90 triangle. So again, we'll start from this 30 degree angle side and get the opposite side identified, adjacent and hypotenuse. So if we took the tangent, or the opposite over adjacent tangent of 30 degrees, and we don't know what the opposite side is because it's this value here, we have to add to the remaining half base section of the two triangles. But we do know what the altitude is. It's 5.64. So now we can easily solve for the opposite side as just the product of the tangent of 30 times 5.64 inches. So we get 3.256 inches as the remaining length of half of the base. So 3.256 inches plus 5.64 inches is half of the triangle's base. So we just multiply that by times 2. So we have a base value of 17.79 inches. Could write that in here. So now we access the area of a triangle formula, which is base times height divided by 2. And we enter in the base of 17.79 inches times a height of 15.54 inches and divide that product into 2, and we calculate the area of the equilateral triangle in the circle, in the 300 square inch circle, as equal to 137.07 square inches. Thank you for watching this lecture and have a great day.